So again, thank you all for coming. This is obviously the first meeting. We have, as you'll see, a good lineup for the next 6 months. So let me move on. This will work. So we already talked about that. So about the club. Let me move this out. Oh, there's the X. Thank you. Yeah. So we will meet the third Friday of every month at 7 p.m. rain or shine, because we'll be doing indoor presentations, and then when it gets dark, we'll be going outside and stargazing. This is a lineup through October. Next month, James Cooper, he led the team at NASA for the James Webb Space Telescope Sunshield. If y'all remember when the James Webb Space Telescope, before it got into orbit, there was this origami of the sunshield opening up. And it's been called sort of the most complex, challenging engineering effort humankind has ever done. And James, who's a Hillsmere resident, was in charge of the team. So he's going to talk about, wow, that's right. Very fortunate. Mark is head of the NASA Science Visualization team. He'll be talking about that July 18th. Lisa will be talking about astroimaging with a digital camera. So you should.
No, I have a camera.
Catherine will be talking about dark sky Maryland and light pollution and what we can do to help abate it. Andy Lomax, who's not a Hillsmere resident, who is with the Chesapeake Bay Environmental Center, he's done a lot of outreach and stargazing events, so he's an expert at showing folks the night sky. So I arranged this so that in October, at this time, it should be dark. So Andy will be out there introducing us to the constellations and so on. As I said, I'm going to be recording these presentations, and I will send you a link. So hopefully I have your email addresses that you'll be able to go back and refresh your memory about them. And I'm hoping every month to cover a new constellation. So as we go through here, we'll cover most of the constellations. And finally, if there's any special events, we may have an impromptu. If there's some spectacular thing happening in the sky, maybe a comet is coming through, we'll do that. We are trying to get permission, by the way, to extend our hours here after 9 o'clock, as well as possibly down at the beach. So Catherine attended the beach committee meeting last week or the week before, and there was some discussion about that. So hopefully, even during these months when it's not dark at 9 o'clock, we can go down to the beach after this meeting, because we have kind of a constraint here in the house to just end the meetings at 9 o'clock. But the board has been very gracious and said if we make a request, we maybe could extend that. So, some questions. Have you ever wondered why Pluto was demoted from being a planet? Every time I do a presentation, that's the first question. Why was Pluto demoted? We'll talk about that. So, a little quiz. If the tail of a comet is pointing up, is the comet going towards us or away from us? We'll answer that question as we go through. It's kind of a trick question, actually. There's always the question, what's the difference between a meteor and a meteorite? We'll talk about that. Why are meteor showers so predictable? Joe was talking about.
Finally get the answer.
Yeah, Joe can maybe answer that.
Yeah, I couldn't even.
So we'll understand why that's true. What is the nearest star to Earth? How do I find the North Star? How did the 12 constellations in the zodiac come to be what they are? What's the song? Right. Those of us of a certain age remember that song. And as somebody indicated, we'll be going over some free smartphone apps. And finally, why do stars twinkle? We'll talk about that. So let's start where we are, right? Which is we're in an arm of the Milky Way galaxy, our solar system. And by our solar system, we mean our star, the sun, which is a star. It's a relatively run-of-the-mill star. As far as stars goes, there's stars that are much, much, much larger and stars that are smaller. So we're sort of kind of in the middle. Of course, in our solar system are the planets, the moons of planets, comets, asteroids, meteoroids, we'll talk about that, and man-made satellites. And somebody mentioned that satellites now are becoming a problem. In fact, coincidentally, last night, I was testing out a camera on my telescope. And this is why satellites are a problem. That star that I was focusing on had a satellite go right through it. And of course, when that happens, it changes the brightness of the star. So if I'm measuring the brightness of a star, and all of a sudden a satellite goes through it, it changes it. So this is the problem. Welcome, ma'am. Thank you. So this is the problem with satellite trails. And in fact, in the images I took last night, there was probably at least half a dozen that had satellite trails going through them. And it's only getting worse. There are thousands and thousands of satellites up there. And there are new also satellite companies that are putting up satellites. So it's just getting worse. So we talk about light pollution on the ground. We now have sky pollution with these satellite trails. And unfortunately, there's been attempts to mitigate it, but still we see things like this. So
we have a lot of non-Americans sending up satellites that are just hanging around up there.
Not as much as the biggest one, of course, is Starlink. That's the biggest. Bezos is putting up one. There's another enterprise that's putting up another. There are hundreds of thousands of satellites that have been up there from other countries, including us, for various reasons. But these low Earth orbiting satellites that have been used for now internet access, which is a good thing for remote, folks who don't have internet access. But the problem is you've got now problems with satellite trails. So let's take a little look at our solar system. The first four planets are terrestrial planets because they're rocky. The next two are gas giants, Jupiter and Saturn, because they're made of gas. And the last two are ice giants because they're made of ice. So at the end of our solar system, we have a variety of planets of different compositions. After Neptune, we have something called the Kuiper Belt, which is where comets live. This is where ice and dusty objects take place. Near the Kuiper Belt is Pluto. Now, why was Pluto deemed not to be a planet? So in 2006, the International Astronomical Union defined a planet to consist of three things. Does it orbit the sun, which Pluto does? Does it have enough mass and gravity to pull itself together as a sphere, which Pluto does? The third characteristic is, does it clear its path in its orbit? Is there enough mass and matter and gravitational strength to push out other things in its orbit? Well, Pluto does not. And for that reason, Pluto is deemed not to be a planet. Now, the irony is in Earth's orbit, there are two locations called Trojan locations that precede and follow the Earth in our orbit. So ironically, the Earth is not clearing its orbit, but that's a little side effect of biases. So yeah, right. So just, that's the reason Pluto was not deemed to be. So it's a dwarf planet, but not a planet. So that's the answer to that question. So also, as I sort of indicated earlier, out of the Kuiper belt come comets. Now, comets go around the sun. Sometimes they don't make it all the way around the sun. But when they do and are traveling back, their tail is still extending out from the sun because of the solar wind and radiation. So if you're looking at a comet in the sky and the tail is up, unless you know where it came from, it could be going away from you or it could be coming to you. And because the tail is not like where it's coming from, it's actually in some cases where it's going. So just a little.
So like the tail precedes the comet?
The tail could precede the comet.
Look like it precedes the comet.
Looks like it, yes, right. So the other interesting thing is there's another belt, the asteroid belt between Mars and Jupiter, and this is where asteroids live. Asteroids being rocky objects that, because of the evolution of our solar system, especially Jupiter's influence, the asteroid belts are where rocky objects live. Now, what happens is that comets and asteroids kind of slam into each other, and what that creates are meteoroids, which are chunks of rock, right? That are just sort of floating around. If those chunks of rock, those meteoroids, come to Earth, that's how we get meteors. We'll talk about that in a second. The other thing that happened just couple years ago, maybe 3 years ago, is we had a visitor from the first time into our solar system. This was an object called, let me get this right, Oumuamua, which is Hawaiian for first visitor. So this was a cigar-shaped object. There was speculation, is this a alien craft or something? Okay. But it's the first time that it entered into our solar system and exited. So
Do they know where it came from?
they don't. They don't. Somewhere, some other star, some other solar system out there came through our solar system for the first time. And then it happened again, I think, a second instance also. So we've had two visitors, interstellar visitors, coming through our solar system.
How did they find it? Like, I mean, was somebody like watching it?
Yeah, it was discovered, I think it was discovered actually by an amateur astronomer. Mark, do you?
Can't quite remember the discovery.
Yeah. So it was just, an object. Amateur astronomers are always looking at changes in the position of things in the sky. And if they see something, they'll go and look and see, let's see, is that in the catalog? Do we know that that's a known object? And this was deemed to be, this isn't known to anything. As they were tracking it and they were tracking the trajectory of where it came from, they realized it came from outside our solar system because they saw its orbit and where it extended. Lisa?
How many miles between Earth and Mars, and how many miles out are the satellites?
Change it all.
Yeah, so between Earth and Mars, I can't.
Oh, because they're going with different.
Well, they're going around the sun in different orbits, so it changes. So the closest approach, I don't know. Now, in terms of satellites, the geosynchronous satellites are like 23,000 miles above here. They're the ones, they're kind of the highest ones that are following the Earth. The lower ones, the low Earth orbiting satellites are much, much lower. Like Starlink, right.
What's geosynchronous mean?
Geosynchronous means that as the Earth is in a particular position in space, that if you put an object there, the gravity of the Earth and the gravity of everything around it will keep it always looking at the same point on Earth. That's why if you have a satellite dish, you're looking at one satellite because it's always tracking that satellite. Now, those are geosynchronous satellites. Low Earth orbiting satellites like Starlink are constantly going around, but they are communicating with each other. So if this is me and I'm looking at Starlink from getting the internet and this Starlink satellite sort of goes away, I pick up the next one. So there's a continuous communication, if you will, of Starlink satellites. So that's why there's so many, because at low Earth orbit, you gotta have more satellites. So there's thousands and thousands now of these low Earth orbiting satellites. And they burn up and they send them up again.
Is it the same as the moon's relationship to Earth and how it doesn't revolve as it orbits the Earth? You always see the same side of the moon.
No, it's a little bit different. The moon is what's called tidally locked. It's such that the same face of the moon is always facing the Earth. So it's in a different orbit than satellites, but it's gravitationally bound to the Earth like satellites are, but kind of a different thing. Okay, so let's go back to meteorites. So meteoroids, again, are chunks of rock that come from asteroids or planets because they're crashing into each other. But also, it could be from a planet. If an asteroid slammed into Mars and a chunk of Mars flew out as a meteorite, which in fact has happened. We've discovered meteors on Earth that have come from Mars. It could be something slams into a moon. So we've got these meteoroids that then enter the Earth's atmosphere, and that's how we get a shooting star, which is the meteoroid coming through our atmosphere and burning up. Okay. Then finally, when it lands on Earth, we call it a meteorite. There's also micrometeorites, which are tiny, tiny pieces that kind of recently folks have found are on the top of buildings. So if you imagine the top of a skyscraper in New York, which nobody cleans, right? There's tiny, tiny pieces of micrometeorites. In fact, there's now sort of a citizen science effort to go to the top of these buildings, look at these little micrometeorites, and try to determine where they came from based on what they look like. So not only do we have meteorites, but we have micrometeorites, and folks are out there as a hobby going to the top of buildings collecting these.
They're probably in your gutter.
Yeah.
Yeah. I know they're in my gutter. I had a lot of-
Too often.
Yeah, right.
I've got to take off our gutter guards.
Yeah. So let's go outside of our solar system. That was in our solar system. So outside of our solar system, we've got stars other than our sun, of course. We have planets going around other stars outside of our solar system, exoplanets. Exo meaning outside of our solar system. We have star clusters. So stars, there are some cases where stars are sort of bound together in what are called globular clusters, for example. Then in some cases, you can clearly see them through telescopes. In some cases, even with your naked eye. There are nebulae, which are clouds of gas and dust that are often a nursery for new stars that have been caused by, let's say, an exploding star. And of course, outside of our Milky Way galaxy, there are other galaxies. What's that?
Beautiful.
Yeah.
Jason, that's beautiful.
So this is the iconic James Webb Space Telescope picture that was taken. I think it was one of the first pictures that was taken, which is a nursery of stars, gas and dust. So this is where stars are born. And the way stars are born is that they start with this gas and dust cloud. They sort of clump together, just gravitationally clump together. They then get denser and denser, and to the point then where the cores condense and a young star is born, and the disk of that dust and gas then sort of spreads out. Think of like you have pizza dough, right? You throw up pizza dough and it just sort of flattens out, right? So this is kind of like what's happening here with another solar system being formed just by sort of the spreading out of the gas and dust. And when that happens, within that sort of spread of gas and dust, planets begin to form. So again, gas and dust, just like it formed the sun, the star in that solar system, begins to form planets. In fact, this is a picture taken with a space telescope. I think it was in X-ray wavelength, that you can see the rings of what are potentially the clearing of path by planets being formed. So this is how planets are formed. And then moons form the same way, like from gas and dust. So everything comes from eventually gas and dust clouds. So as Carl Sagan said, we're all made of stardust, right? Because everything on Earth, the elements that are in us come from exploding stars. So that's where we are. So a little bit about stars. When you look up at the night sky with your naked eye, the stars you're seeing are only the brightest stars in the Milky Way. We're not seeing stars from other galaxies. They're too faint. So it's only stars in the Milky Way. Stars come in different colors, size, temperatures, and ages. There are over 100 billion stars in the Milky Way, and it's estimated that there are over 1 septillion stars in the observable universe. Now, observable universe means we can only see back so far. James Webb telescope has extended that, but 1 septillion stars. So if every star has at least one planet, or most stars have at least one planet, that says there are at least 1 septillion planets, 18 zeros, right?
Yeah.
So there are that many planets out there other than us. So it makes you kind of blow your mind about Lisa.
The sun?
Very good. We are an exoplanet to an alien in some other solar system. Absolutely. Yeah, because we're outside their solar system. So we are, to them, an exoplanet.
An exoplanet to the sun. Because the sun.
Yes, we are an exoplanet to our sun from somebody else in another solar system. Yeah.
So an exoplanet is not a special planet.
No, good question. Exoplanet is not a special planet. It's just the name of a planet outside of our solar system. It could be, an exoplanet could be the size of Jupiter. It could be the size of Earth. So yes, it's not a good question. It's not a particular kind of planet. It just means it's some planet. Now,
At the beginning, Dennis gave you the explanation for Pluto. And one probably unintended consequence of that is one of their criteria was that they had to orbit the sun. So they made all of the exoplanets not planets. It's a problematic definition.
I see.
right. Yeah, yet to be determined how they're going to
Yeah.
characterize
They're trying to fix that, yeah.
exoplanets. Yeah. So let's talk about the night sky and the apparent movement of stars due to two things. The Earth is rotating, as we know, and the Earth is going around the sun. So there's changes in seasons. So if we look at the Earth, we are, of course, slanted. The axis of our Earth is slanted. So we're rotating in sort of a slanted direction, as you see. So the axis of our rotation is pointing to Polaris, which is the North Star. There are other stars up there, right? But because we are rotating in a certain direction, when we're looking at stars throughout the night, it appears that they're going in the opposite direction. So if you were to take a look at stars, this in fact is north this way. If you take a look at stars, you'll see that they are over a course under the course of the night going this way. They're kind of rotating around this way. In fact, if you put your camera looking at Polaris, which is, directly north, and the Earth is rotating around it, a star will tend to go around Polaris. If you take a long exposure of Polaris, like maybe Lisa has done, you see this sort of thing, right? Which I'm sure all of you have sort of seen. So this is because you're looking at Polaris, the Earth is rotating, but the appearance is that the stars are moving, but the stars really aren't moving. We're moving. So, now around, if you imagine there's a globe around us, we call that the celestial sphere. And that sort of globe around us, which all the stars are sort of in this globe, cutting through it is the celestial equator. So everything revolves around the celestial equator. So the stars appear to be just revolving around in that direction. Now, of course, we and the planets are orbiting the sun, but we're orbiting the sun in this direction. So the ancients our ancient ancestors saw stars moving in this sort of circular direction if they were looking at the North Star. But then they would see these planets and the sun and moon sort of go in a different direction because they're going across. They're not following this pattern of the Earth rotation. So our ancient ancestors saw the moons and the moon, the planets, and the sun behaving kind of differently across the night sky. They weren't following the same pattern as the stars. So that was what led to legends of, the planets and so on. So we're going to talk a minute about the zodiac, but imagine the fact that the planets and the moon, for example, are cutting through different constellations as they're orbiting. So keep that in mind. Now, a little bit orientation. So if you were to go out and start stargazing, this is a Google map of Hillsmere. And the Hillsmere Drive, for the lower part of Hillsmere Drive, is almost directly due north and south. We are where that little red thing is. And so pointing that way is north. So if we ever go out here, if we ever go out and take a look at the sky, we kind of know north is that direction. The interesting thing is we live where this little blue thing is here, and we live on Mead Drive. So one would think that if you look at out our back window, you're looking north, but it's actually kind of that way. So Joan and I always have this discussion about where north is. Yeah, right. So anyway, so that's just a little side thing about knowing where north is generally helps out to find what we're going to talk about, which is the North Star. So let's talk about constellations and asterisms. So a little background, as I said, our ancient ancestors ascribed different meanings and stories and names to groups of stars as they moved in the sky, the so-called constellations. Particularly significant were the 12 constellations where the planets and the moon went through. And those 12 constellations are the zodiac. So that's where zodiac came from. And the constellations move not only during the night around Polaris, but they also move during different seasons of the year. So it's not just moving around with the Earth's rotation every night, but also because of the season of the year, because we are now in a different location in our orbit around the sun, the constellations are going to appear in a different location. An asterism is just sort of an interesting pattern of stars that may span constellations, that may be within one constellation. We're going to talk about probably the most popular one next. So the constellation for tonight is Ursa Major, the Great Bear, and the little asterism in it is the Big Dipper. So that's where the Big Dipper is. So our ancient ancestors ascribed this sort of pattern of stars to a bear. We, more modern folks, have said that looks like a dipper. So we've named it the Big Dipper. Now, the good thing about the Big Dipper, as we'll see in a minute, is that it helps us point to the North Star. So let's take a look at the Big Dipper. So if you look north, right now, the Big Dipper is straight overhead. You kind of have to crane your head up there. You'll see the pattern pretty clearly. It may be kind of in a different orientation. In fact, it is. I was looking at it last night. And there are stars in it that are brighter than other stars. So these are the two brightest stars. And then the dimmer stars, and the dimmest is the one you see here. But all of these can be seen with the naked eye after you have sort of let your vision get used to the night sky. After about 10, 15 minutes, you'd be able to see it up there. Now, the two stars at the end point to the North Star. So the good thing about the Big Dipper is if you find the Big Dipper, then look at the two stars and follow that path to the North Star. The North Star being dimmer than we often think. Joan?
I have a real problem with Polaris because I thought it was supposed to be a big deal. It's like you can barely see it.
Yeah, it's very
So
faint.
It's like, so what?
Yeah.
That's all.
Right. But it's an important star.
Yeah.
Right. So the other constellation is Ursa Minor, the Little Bear. And in fact, you can see right away, this is the Little Dipper. So in the night sky, and by the way, the tail of the Little Dipper is Polaris. So if the sky were clear tonight, May 16th at 9 o'clock, and I was looking north, you would see the Big Dipper straight ahead. You would see the Little Dipper below. And if you followed the line through the Big Dipper, it would end up at Polaris. So that would be if we saw it tonight. If we came back at our next meeting in June, because of our rotation around the sun, at the same time at 9 o'clock, it's going to be a different orientation. But it's sort of moving itself around Polaris. So again, the orientation changes with seasons of the year because of our movement around the sun, but you can still use it as a finder for the North Star. So what can we do backyard observing? Well, the easiest is just naked eye observing. Just get out there. There's some apps I sent around to help you do that. Using binoculars. Lisa's going to talk about using a digital camera. I'll show here a little bit later what's called a smart telescope, which is a very small telescope about this big that is the latest thing out there for, I'll call it casual observing by non-amateur astronomers. It's very easy to use. It does great images. If we have time, I'll take it out and show you.
How much does it cost?
$549. But a lot cheaper than, a lot cheaper than big humongous telescope. But it's a great, very user-friendly telescope. And of course, then a conventional telescope. This is my telescope in my backyard. Could be used for visual observing, astroimaging, or science. So from my backyard in Hillsmere, I'm part of the NASA exoplanet team. I can detect an exoplanet. And the way I do that is I'll be looking at a star like that one that had the satellite go through it. I'll be looking at a star throughout the night. And if there's a dip in light of the star, that is the indication of an exoplanet that had gone across that star. So from my backyard telescope in Hillsmere, I can detect a planet going around a distant star. So what can be done from Hillsmere? All of the above. You can start with just naked eye observing and just get more into it. And if any of you know anybody who has a telescope who hasn't used it or is interested, one of the things we hope to do in the club here is to help folks become more proficient with their telescopes. So, or if you get a new telescope, bring it out on a dark night and we'll help you go through it. A little bit about terminology before we get into the apps, because you'll see these terminology in the apps. We talk about transparency as the effects of clouds and dust, wildfires, that sort of thing that sort of affect the visibility that we're looking through. Seeing is turbulence in the atmosphere. This is what causes stars to twinkle. So we astronomers don't like twinkling stars. So, because it's just turbulence. In fact, if you ever look at Jupiter through a telescope, it's just sort of wobbling around like that. So there's a process for taking images of it, but it does affect the imaging. So elevation, most of you I'm sure know, it's the degrees up from the ground. Azimuth is the degrees from north, sort of the compass direction. And I'm saying these terms because some of the apps use these terms. Excuse me, magnitude. You hear that a star is of a certain magnitude. Astronomers use this as a measure of brightness of an object. The interesting thing for historical reasons, the more negative magnitude, the brighter. So I know it's counterintuitive, but that's the way it is. So the sun has a negative 26 magnitude. Neptune, which is very faint, has a magnitude of 7. Here in Hillsmere, in fact, Catherine and Mark and Lisa and I were out at, I think, at Quiet Waters, and the most magnitude or the faintest we could see was about 4, maybe 5. So anything beyond that probably can't see with your naked eye. So Neptune, forget it. Certainly Jupiter, Saturn, is possible, but some of the fainter planets you can't. So, and of course, the more light pollution, the more difficult. So, that's the way it is. Okay, so the card that I passed around, we're going to go through each of these quickly as the apps. By the way, that first one, when you go to load up that app, it's a small I. So small I CSC. This is the Clear Sky app. This gives the visibility at a certain time. Sky Safari is good for locating objects, and the ISS spotter for finding when the International Space Station is going to be overhead. We're going to go through each of these in a second. A website you might want to look at is called spaceweather.com. You can sign up for alerts. So if there's, for example, an impending solar flare happening, you get an alert. It'll tell you if there's any strange things happening. We're finding some interstellar object coming through. So it's a great site for just kind of staying on top of what's going on. So if we go through each of these apps real quickly. So this is the Clear Sky app. So this is tonight, right? Friday the 16th. The forecast, of course, cloudy. So the bottom darkness one, which is, let me use my cursor here. This bottom one, this is showing where it gets dark. So you can see around 2000, 2100. So 8, 9 o'clock is when it's dark all the way through the night. So this is when viewing is best. So you would look up and you would see what's happening during that time. Well, obviously, right now around 7 o'clock, which is around 1900, it's cloudy, but it looks like things are going to get a little bit better. Clouds are going to clear up, but this ECMF is a European model of clouds. So that's saying still cloudy. But tomorrow night looks, a little potential of good around, what would that be? 9, 10 o'clock. So this is a great app for forecasting when it's going to be good enough to see with your naked eye. Yes.
So which one are you using to get that?
So
I'm on the app, United States, go down to view, choose.
And by the way, when you use the app, the best location, you'll ask you which location you're at or want to. I would say select the U.S. Naval Academy. And there's also a little arrow in the upper right that you could click to give you what's nearest to your location. So that is a great app. It's pretty accurate for looking at when things are going to clear up. The other app for again, free app for navigating the night sky is Sky Safari. And if you go down and click the search button, let's say you want to find Polaris. Okay, you know it's kind of out there somewhere in the north, but as Joan says, it's so faint that, you know, you really can't find it, even maybe with Big Dipper. So you would hit search, you would type in, or you would put in Polaris, which it knows Polaris would be a name that it would know. And it would then come up with two objects. The interesting thing is there's a Polaris in the southern hemisphere. So got to make sure you hit the right Polaris, which is what you see there. So when you click that, you then get information about Polaris. And in the lower left, if you now want to start finding Polaris, when you hit center, it's going to start giving you arrows where to go. So if you hit center, it's going to say, okay, move over a little bit more, and then up, and you're now at Polaris. So the arrows will sort of navigate you to where Polaris is. So you can do that for planets, for for stars, for constellations, and so on. The last app is the International Space Station Spotter. So what's nice about International Space Station is it's a very bright looking star, if you will, that is just going across the night sky. And when you imagine there are people in it, it's pretty cool to see that object going across the sky. So what this app does is it will first show you the current location, but it will, when you hit forecast, it will tell you what is upcoming. So I did this earlier in the week, and May 13th, which was 3 days ago, the stars indicate how good it is. 2 is okay, it's not great. 4 is fantastic. 4 means it's like really visible, kind of a long path. If it's like 2 stars, it's sort of low on the horizon. You may or may not catch it. So if I wanted to check on May 13th, if I'm interested in observing it, I would click that. And what I would get would be this screen. I'm going to kind of zoom in on that middle part now because it's a little bit small. And what this screen shows is, first of all, compass direction, where it starts and where it ends. So the compass would be, this would say it's going to start in the west, and it's probably a little bit northwest. It's going to end kind of northeast. It's going to be at its highest at an elevation of 31 degrees. These trees out here are about 30 degrees, so it's kind of, skimming the trees. Magnitude minus 2.3, which, as we said, that's bright enough for us to see. And the lower boxes indicate where it starts. So it's going to be 10 degrees in the west, and it's 719 miles from us. Somebody asked, how far are the satellites from us? Well, the International Space Station at that point is 719 miles. At its peak in the northwest is 468 miles, and then it's 1,400 miles. So this kind of gives you where to start looking, how high above the horizon will you see it, and how bright it is. So every month we'll talk about what's up for the month. I say maybe because we've been looking at this happening for months and it's overdue. There's an explosion overdue in the constellation Corona Borealis. A particular star there, T Corona Borealis, is expected to brighten from 10 to +2. So it's like right now at 10, we can't see it. It's too faint. At 2, we'll be able to see it. So all of a sudden, there'll be a new star in the sky. It's going to be about as bright as Polaris, or as dim as Polaris. But it will be visible with the naked eye. And this brightening happens every 80 years, or just about. So the last was 1946, before I was born, or John was born. So depends on where Corona Borealis is. So if you use the app and put in the constellation Corona Borealis, at whatever time of the year you're going to be looking, it'll show you where to look. But it will be in the news big deal. This is a big deal. And amateur astronomers are literally on their phones, on alerts, waiting for it to happen. Professional observatories will all of a sudden be looking at it, looking at the increase in brightness and the decrease. So it's a big deal.
How long does it last?
That's a good question. A few days, Mark, Amanda, do you guys know?
I think it's longer than that.
I know it goes up very quick. I'm not sure how
I
it,
think it's months.
okay, yeah. So this is something that our ancient ancestors all of a sudden would see, like something happening, an explosion or something, and assign some.
It's gonna show.
No, it won't be an explosion like that. It would just be all of a sudden, bam, there'll be a new star in the sky. So you'll see this in the news. It was expected to have happened last year. People are still waiting for it, but hopefully it's going to happen. So now, to answer the question, Corona Borealis during May and June is overhead. So, but if you use the app, you'll be able to see exactly where. All right, so back to the questions we started with. We know why Pluto is not a planet. We know why tails of a comet don't really tell you which direction it's going. Talked about the difference between meteor and meteorite. We didn't talk about why meteor showers are predictable to a great extent. It's because a comet like Halley's Comet, many years ago had gone through, crossed the orbit, our orbit with the sun at a certain place. Well, when it did that, it left all these chunks of meteoroids. So at a certain time every year, we'll go around the sun and we slam into those little meteoroids, we get meteor shower from Halley's Comet. So it's very predictable because we know where that clump of rocks are. So we answered that question. What's the nearest star to Earth? Or sun? But the nearest star is Proxima Centauri, which has a planet going around it, 4 light years away. So the star nearest to us, other than the sun, has a planet. However, that planet is probably getting cooked because it's too close to its star. So many of these exoplanets are planets, but they're so close to their host star that the radiation and such is not going to make life habitable. There are exoplanet systems where there have been 6, 7 planets that are in the so-called habitable zone, which allows for liquid water to exist on the surface, and where they're a little bit further away from radiation from their stars. So there is the potential. But if there's 1 septillion planets, it's likely that there are some habitable ones out there. We just haven't discovered them. So how do we find the North Star? We talked about using the constellation, the Big Dipper, for example, and Little Dipper. We talked about the zodiac, which is the constellations that our planets and moon go through. And we talked about the useful apps. So stars twinkle because of atmospheric scintillation. So that's it.